Thank you for the kind introduction, Jing. Thank you for having me. Unfortunately, I had two videos that I insert into my PowerPoint, and it's not compatible with my MacBook. So that's why I have PDF. So we're not going to be able to see the videos, but I'll just tell you the stories. What I'm going to talk today, I'm going to share a recent publication on the rate of oil depletion from lubricated surfaces during slips condensation. I'll explain what slips condensation is. Okay, so the motivation for this work is condensation, which is ubiquitous both in nature and in industry. We see condensation in nature when we have a cold beverage. On the containers, we see droplets on the outside, or during a humid day when fog forms on our windshield glass. Condensation is also an essential process in steam cycle, typically called in thermodynamics Rankine cycle, refrigeration systems, or heating, ventilation, and air conditioning. These large-scale processes improving the efficiency of the overall energy efficiency by a small percentage would have significant impact on the globally on the energy utilization. And for that reason, phase change condensation, this is phase change from the vapor to the liquid phase, has been studied extensively for over a century. Broadly speaking, there are two modes of condensation. This is what I had the video. Unfortunately, you're not able to see, but when the surface is hydrophilic, due to the high surface energy of common heat transfer metals such as copper, aluminum, stainless steel, nickel, the vapor condenses by forming a continuous liquid film that's commonly referred as film-wise condensation, and the continuous growth of this thin liquid film hinders further heat transfer. And for that reason, the heat transfer coefficient, which is the amount of heat that we can remove that's rejected by the vapor per unit area, per unit temperature difference, is very small for film-wise condensation. This can be improved by hydrophobizing the surface, in which case vapor condenses by forming discrete water droplets that leaves when they reach the capillary length for water about 2.7 millimeters. What that means is the vapor that forms on the surface leaves the surface at an earlier, it doesn't form a continuous liquid film. For that reason, this condensing surface is exposed to vapor, and therefore the heat transfer coefficient is significantly higher, typically about 5 to 7 times, as much as an order of magnitude larger. So if you look at film-wise condensation, the heat transfer coefficient is in the order of about 10 to 15 kilowatt per meter square Kelvin, but dropwise condensation could go as high as 80. When the surface is nanostructured and lubricated with oil, due to enhanced droplet mobility, the droplets, they shed faster, and at a higher frequency, the heat transfer coefficient increases by about 30%. The reason for being the same explanation for the dropwise, where when the droplets leave faster and at smaller length scale at higher frequency, the surface is exposed to vapor, and therefore the performance improves. So this is an SEM image of the nanostructured surface that's impregnated with oil for the condensation for the condensation experiment. So one challenge with this, even though the heat transfer coefficient is significantly higher compared to film-wise, or 30% higher compared to drop-wise, one challenge with the slips condensation is that when the droplets leave, they shed, when the droplets shed, they deplete the oil, and the lifetime of these surfaces is relatively small. There are few works that shows that the surface the oil depletion is so fast that the heat transfer coefficient decreases by more than 80% in the first 3 hours. And this indicates the challenge of integrating or even integrating these systems into industrial applications, which requires larger lifetime. And therefore, the object of this work, what I'm going to talk today, is to understand how the oil depletion occurs during condensation. That's on slips condensation. What's the mechanism for the oil depletion, and if we can develop a model to better understand the rate of oil depletion from these lubricated surfaces. So this is a copper tube, and cold water is flowing through this, and the condensation happens on the external. So what I'm going to speak with you today is show you some experimental characterization and our modeling efforts. And so the experiments are pretty straightforward, where we have the nanostructured copper tube attached into a liquid flow line. The cold water comes in and then goes out through this way to, if we're interested in measuring the heat transfer coefficient, we measure the temperature at the inlet and at the outlet, and we get the amount of heat that's rejected by the vapor from MC delta T. And we can also measure the vapor temperature and the humidity in the environment. But typically the experiment is the sample is attached, the sample is nanostructured like this, and then lubricated with oil. The excess oil is removed by positioning it vertically for over 12 hours. I typically do this lubrication 12 hours earlier than the experiment. So after the sample is attached, cold water is allowed to flow, and vapor is introduced from a vapor generator. The vapor generator is basically a container with water filled and with a heater from outside. And so we boil the water and then generate the vapor that's gonna go into the chamber. And we capture images using a high-speed camera here as shown. So this was, and again, the high-speed video that I wanted to share with you. Unfortunately, you wouldn't be able to see, but I'm going to show in the next slide the high-speed images. But what we wanted to see is when these droplets are falling due to gravity, what we wanted to see what happens or what's left behind when these droplets fall. And so this is the time-lapse images where the droplet is, the vapor is condensing and the droplet is growing. It forms this neck region and the droplet breaks unequally, a small droplet that's remaining on the surface and the larger droplet falling. And when this larger droplet that's falling, we call it pendant droplet, and the droplet remaining on the surface, we call that one satellite droplet. And we wanted to see what happened, the first thing is we wanted to see the identity of this droplet. It's really difficult from the white light images to know if what's left here in the red box, if it's water or oil. So this is a magnified image that shows what's left behind the satellite droplet. And therefore, to identify if the satellite droplet is water or oil, we add a fluorescent dye on the water. And when this water droplet is falling, the water droplet is fluorescing because we added a fluorescent dye. And what we saw is that the small droplet that's left behind when the pendant droplet falls is water, as you can see here. This is the white part shows that this is the water that's fluorescing. A magnified image is shown here where you can clearly see the satellite droplet, which is water, and the wetting ridge. This is like the curved oil surface that surrounds the droplet. And this experiment clearly indicates that the droplet that's left behind is water. And to ensure that the systems are equivalent or we're not distorting the experiment, we measured the surface tension and the viscosity of water when we add the fluorescent dye with and without the fluorescent dye. So the fluorescent dye we added is only 0.28%. And this is pure water, 0.8% that's the water without the dye. And as you can see, the surface tension is nearly identical within the measurement uncertainty. And so is the same for viscosity. Actually, for both the surface tension and the viscosity, the change in surface tension and viscosity was less than 10% by adding this fluorescent dye. So the next thing we did was previously, if we dyed the water, in this next experiment, we dyed the oil using a UV dye to see the mechanics when this droplet is falling, the pendant droplet is falling. So this is an experiment where the dark side, the white arrow, is the water droplet, and this dyed section, the bright section, that's the oil. And when this droplet is falling, it grows large and it falls due to gravity. And this oil, the wetting ridge that forms underneath the droplet, that surrounds the droplet, it rearranges itself. It's stretched when the droplet is falling. You can see that this droplet is almost like a large vertical falling down, and the wetting ridge was stretched, but it rearranged itself after the droplet departed. And similarly, we added a 0.28% UV dye for the lubrication oil to make sure that we're characterizing the same system. We measured the surface tension and the viscosity of the oil without any dye, that's 0.08%. And when we add 0.28% dye into the oil. And as you can see, the surface tension, both surface tension and viscosity, is nearly the same, less than 10% difference. So the next thing that we did is, now that we know the identity of the satellite droplet is water, and we saw that the wetting ridge after the droplet departed rearranged itself, we wanted to measure the rate of oil depletion, how much oil is depleted when these droplets fall. As I mentioned in the motivation section, one of the challenges with this slip system is when these droplets eroded the oil, the performance degrades. So that's a major concern. For us, we're interested to know how much oil we're depleting with these falling droplets. To do that, we did the thermogravimetric analysis, TGA. This is a system where if you have a mixture of different liquids, you evaporate them sequentially at different temperatures, and by by measuring the change in weight, you would be able to see the percentage composition of each component. So in this example, this is our TGA protocol where we have the mixture and we ramp the temperature from room temperature to 100 degrees C. And we maintain that temperature for about 25 minutes or so. And then we ramp the temperature to 300 degrees C, and then we maintain it at 300 degrees C for about 10 minutes. What this protocol does is when we ramp the temperature from room temperature to 100 degrees C, remember what we're capturing during our condensation is the droplet falling, and basically it's an oil water mixture. So during this 100 degrees C ramp up and maintaining that for 25 minutes or so, all the water in the mixture evaporates. And then we ramp the temperature to 300 degrees C, where we were able to evaporate the oil. So this is a typical experiment. So this is the protocol. The second image shows you a typical oil water experiment, how it evaporates. So during the first ramp up and maintaining at 100 degrees C, as you can see, the weight decreases. And then after about 10 minutes, it's almost constant, indicating that almost all the water has evaporated. And then during the second ramp up, during the second ramp up or the third stage 3, we see another drop down for the oil. And then finally, all the oil and water evaporates in the system and it becomes 0. And so by so doing, we're able to see during the first decline here, we're able to quantify how much water we have in our mixture. And then when the second drop down occurs during the third stage, we're able to quantify how much oil is depleted depleted by the falling droplet. And so in our experiment, we fabricated these copper tubes. We lubricate them with oil. As I said, I typically prepare them way earlier, 12 hours early. So at T is equal to 0, before I start the experiment, I measured the difference. So I fabricated the copper tube. I measured the mass, I measured the weight, and then I lubricated it, waited for 12 hours, I measured it again. The difference in weight would give me the amount of mass, the mass of the lubrication oil. Since I know the density, I can get the volume of the volume of oil impregnated onto the copper tube. That's the volume of oil impregnated at T is equal to 0. And then after a 10-hour experiment, we did this condensation experiment continuously for 10 hours. I measured the mass again. Since I know the initial mass, the difference in mass is the amount of oil that's depleted. That's at T is equal to 10. And I also collected these falling droplets individually, and we measured the amount of oil in those droplets using our TGA technique, which I just showed in the previous slide here. And therefore, few points here is the rate of the amount of oil depleted by these falling droplets. It decreases as time goes by. This is evident since initially we might have an overlayer on the system, and as time goes by, the lubrication oil infiltrates into the system, it's immobilized by the nanostructure, and the depletion rate was small. And importantly, since I know the shape of the tube, I can also calculate the thickness of the lubrication oil as a function of time. And one thing that we observed is we varied the viscosity of the oil. We used different oils, Krytox 104 to 107. The variation in viscosity is order of magnitude between these two. And we saw almost no variation, no difference in the amount of volume that's depleted during our condensation experiment. And importantly, this lubrication film thickness that I found from the TGA measurement flattens out about 3.7 micrometers. And this is an AFM of the microstructure surface. They actually agree, they pretty much are the same, indicating that initially the reason we have high oil depletion is it's an overlayer above the nanostructure. After we depleted those, the oil on the surface is infiltrated inside the microstructure, and it was immobilized by capillary forces, and that was the reason that it just flattens out at the height of these micro nanostructures. And the last two slides, I want to show some modeling efforts. This is very, we can draw an analogy between the Landau-Levitt drawing problem and these water droplets from the lubrication tube. It's spherical, but when the droplet is falling, actually, it stretches down, behaving like a flat plate. And when a flat plate is pulled from a viscous liquid, the Landau-Levitt drawing thickness, that's the equilibrium thickness far from the bulk liquid, it scales with the capillary number raised to the third, capillary number raised to 2/3. This has been, this is a theory that's been for a very long time, has been validated. But the analogy between these two is that this droplet, when it's falling, it stretches this lubrication film. It stretches it in the vertically down direction. But because this wetting ridge is at lower pressure than ambient, the lower pressure region also pulls the lubrication upwards. So basically what this model implies is that the balance of forces between the weight of the droplet shearing the oil and the low pressure region in the capillary region pulling the lubrication oil, the balance between these two determines how thick this Landau-Levitt drawing, the equilibrium thickness is, which we call an oil skirt, the thickness of the oil skirt. So it's determined by the balance of forces between the low pressure region and the weight of the droplet. So what we did on our model is that the amount of oil we lose, it scales with this capillary, the Landau-Levitt. So the oil depletion scales with some characteristic area, which we scale it with as R squared. R is the radius of the droplet, and the Landau-Levitt drawing thickness, the equilibrium thickness. And we change it in this proportionality into a constant using beta, and we got this expression. And for all the data we got, we non-dimensionalize it, which I don't have time to talk here, but the non-dimensionalized form of the oil loss is, and this is the non-dimensional quantities we got from Buckingham-By theorem. They agree pretty well. And we got these constants from the Buckingham-By theorem. And we also compared it with our model, and our model, which is this V loss is our model. And we actually measured from our TGA experiments, they agree reasonably well. And by fitting a straight line, we got this beta constant that we used for the proportionality constant. And the results from this modeling matches exactly the results we got from this Buckingham-By theorem analysis. And the last thing that I want to show is there is some concern that the oil loss is due to oil spreading on the droplet. To answer that, we actually used two different oil. I used mineral oil and Krytox oil, where Krytox oil, there is oil spreads onto the water droplet due to the positive spreading coefficient, and mineral oil doesn't spread on the surface, on the oil droplet. And this is an experiment that we did where we showed indeed there is a spreading layer on Krytox, but not on mineral oil. But the oil loss that we measured, the amount of oil depleted from the surfaces between mineral oil when there is no spreading and Krytox oil when there is spreading, they're pretty much the same. We didn't see much difference. It's within the measurement error. And lastly, we measured the radius, the departure radius is the same when we vary the viscosity, as well as in the presence or absence of, in the presence and absence of oil spreading onto the water. And the last point here is between oil slips and the dropwise condensation, we saw a 50% decrease in the departure radius. And that we believe is the reason that we see high heat transfer coefficient on slips condensation. So to summarize, I think I showed in this work, we showed that the droplet that's left behind, which is called the satellite, when droplets are falling, they leave a satellite droplet behind. And the identity of the satellite droplet is water. And we showed that the over 10 hours of condensation, the lubrication film thickness, the B that I showed, it goes from about 6 microns to around 3.7 microns. So we saw a 50% depletion over 10 hours. This is significantly higher than what has been reported previously. And we attribute this to the nanostructured surface on our tubes. And one important result that this work shows is that the wrapping layer, which is oil spreading on the water, it doesn't have much importance in terms of rate of oil depletion. Its contribution is minimal, if not none. And we saw a departure radius for different viscosities in the previous slide. It's the same. It's independent of the absence or presence of spreading layer or the viscosity of the oil. And with that, I would like to thank, this work is mostly done when I was at Harvard. This is the group that I worked with. And I would like to thank my advisor, Joanna, and some of the funding agencies that funded this work. And I would be happy to take any questions that you may have. Thank you.
Thank you. Thank you, Solomon. It's much detailed presentation than I heard like a year and a half ago. That's very nice. Thank you. Anyone has questions? You can raise your hands or type your questions. Maybe I can just ask my question first, then anyone else you can jump in. So for like 10 hours of the depletion, and you saw the lubrication is stabilized.
Yes.
So how does the heat transfer coefficient change over these 10 hours?
Actually, that's a good question. I think the focus of, so if you look at these images, the initial thickness when I start the experiment is about 7, I would say. So, and then after 10 hours, it's about 3.7. This result, the two important results are, like, the first one is the height of the microstructure is about 3.4. So initially I have an overlayer that's depleted by the droplets, but in the later hours, the oil, it recedes into the nanostructure and it remains there, immobilized by the nanostructure, and it's almost the same. So that's one. And the second one, the one that you mentioned actually, how the heat transfer coefficient measures. In our work, the focus was understanding this oil depletion. So for that reason, I didn't measure the heat transfer coefficient. That's something that I would be interested in doing, like in continuation of this work. But that's a very excellent question, because previously some people, they have shown that the heat transfer coefficient decreases in less than 3 hours. But ours, over 10 hours, it was very stable. So measuring the heat transfer coefficient is definitely of interest going forward. Thank you for asking. That's a good question.
Yeah, that sounds reasonable, because your research focusing is on the durability part. So
Yes.
I was following up on the durability question, like so you see the satellite droplets, like when the droplets, the condensed water droplets leaves the surface. So how does the satellite droplets, is it good for heat transfer coefficient, or is it good for durability? How does that affect the durability or the heat transfer when we have a satellite droplet?
Actually, this is very insightful, good question. So the satellite droplets actually are very useful. The reason for that is you see this curvature shape the shape by itself, it tells you that this is at lower pressure than ambient. So the reason that these satellite droplets are useful is they create this large pressure difference at the oil ridge that holds the oil together. And therefore, so they're very useful. When the droplet is falling, the reason that we're losing oil is because of the shear force, but they counterbalance that shear force. And because of these satellite droplets, the oil is held in place, or it avoids this being depleted by the droplets. Therefore, just to answer, the short answer for that one is the satellite droplets are indeed useful. They create this low pressure region that helps to slow down the depletion. It happens naturally, but it's a useful thing that it happened.
Can we control the satellite droplets and geometry of size to further help the durability?
I think not that I know of. I think these are like these droplets are these satellite droplets. They're not in contact with the solid surface because there is a very thin film layer, and they're basically floating on this oil surface. So it might be of interest to if we can use external forces in terms of retaining them. But I think it just happens as a consequence of the condensation process. I don't think we need to do much to maintain them on the surface. It's just the pressure difference will always split the droplet unequally, letting smaller droplets remain on the surface, which reduces the oil depletion.
I see.
But it would be of interest if there are some external ways to control them, or to even increase their number or frequency. If there are some manipulations that we can do, that would be that would be interesting.
I see. Thank you. Thank you very much.
Sure.
So I don't have further questions. So anyone else has questions?
Hi, I have a question, Jing, if time permits.
Okay.
Yeah, go ahead.
Hi, Solomon. This is Robin. And in terms of durability, let's say you have a surface that is under mechanical load,
okay,
especially fatigue, cyclic mechanical. So
yes.
how does that affect? So how does that affect the lubrication and also all of these behaviors of droplets leaving the surface?
If the surface is under fatigue?
Yep.
I think one thing that I would say is, so I'm in the impression that fatigues and this kind of processes might create some roughness on the surface, some when the surface fatigues, there might be some cracks on the surface that actually is useful in terms of retaining the oil. So basically these surfaces, these lubricated surfaces, the oil is held in place because of the nanostructures. They form this meniscus shape that holds it together, that immobilizes it. So in the presence of fatigues and cracks, I think the lubrication is more stable. It remains on the surface more than just having a flat surface without the without the cracks. Did that answer your question?
Yeah, I see. That's very interesting because, well, you can also imagine over a very long term, of course, it fails. But I think in the short term, you mentioned it facilitates. I think that's a very interesting question. Thank you.
Yeah, it has. So the little use, these slips are basically most of the time they're used for they're for condensation, reducing friction. So when you see it from reducing friction from mechanical standpoint, reducing solid liquid contact, in the presence of those solid contacts, if you create some cracks and roughness on the surface, having the lubrication is actually, it just infiltrates into those systems, and then it will inhibit the solid-solid liquid contact. So from that standpoint, it's advantageous. And the good thing about all these slip systems is they're self-regulating. Whenever you have new cracks and new scratches, they infiltrate those areas and they fill those voids and areas.
That's a good point. Thank you.
All right, thank you for your question.
Okay, so any more questions?
Okay.
Okay, so if there is no more question, let's thank Professor Samuel Andrew again, and so let's move on